Okay, and now this is the wavelength versus frequency. And the graph that your Desmos, or the graph that you should have ended up making, should have looked something like this. And so once again, this is your X and this is your Y. Make sure that we are, or that you are, renaming your X to whatever it's supposed to be, and that your Y is supposed to, is also renamed. Based on what we had left you, your X is going to be your frequency, and your Y is going to be your wavelength. Okay, and the symbol for that is a lambda. Now, the kind of graph that this has made is what we call an inverse relationship. And the inverse relationship just really means that as your X is increasing, as this is increasing, your Y is actually decreasing. So it's going down. And so we can model that using a relationship. So whenever you increase your denominator, what ends up happening is that the overall number will decrease. So when you make this, the bottom number, the denominator, bigger, your Y will decrease. And the other part of it is that we call this K. Sometimes it's 1, but it's not always 1. We do know that it is a constant. It's some number that doesn't change. And in this case, we're going to talk about what that number means. So let's go to the mathematical relationship. So in Desmos, you might have put in y sub 1 tilde k over x1. And so then what you actually type in is what the equation really stands for is y is equal to k over x. And y is our wavelength, and x is our frequency. So we're just going to replace what y and x are. So y was our wavelength, and we had a constant over our x, which is frequency. Okay, or if we want to write it out, it's wavelength is equal to, let me use blue, k constant over our x, which is frequency. So when we rewrite it just with the symbols, we have wavelength is equal to our constant over frequency. And so this should be the final equation. It should be the last line for the mathematical relationship. So this part will all go in the mathematical relationship in the super summary box. Okay. Be prepared to know what all of this means. So remember that this is what we say the parent equation for inverse, and then we replaced the placeholders with what they mean, and so we get our final equation. So now what does that mean? What is the quantitative relationship? Since it's not as clean as the slope, remember, so as x increased by some number, y also increased by some number. And since it's not the case, we have something a little less clean. So we have this. So what we're going to do is answer a couple questions. What does k represent? So we know that k means a constant. So this is you. So now you got to think. Okay, this is you thinking. What remained a constant? during the lab, or between wavelength and frequency. Okay, so what's the thing that remained the same? So the answer would that be is our string. Okay, our string remained the same. So our string vibrated back and forth, and so it created the shape where we have a node here, and we have a node here, and we have our antinode here. And so that would be the first harmonic. And then the second harmonic maybe would be like this, would be more even, and so on and so forth. So, but what remained the same is the string. Okay, the string remained the same. And what that meant is our string's wave speed, how fast the string was moving, the velocity, which we also called the wave speed, stayed the same. And so when we put our information into the equation, so we had our wavelength, which has a units of centimeters. For your lab, you measured in centimeters. And our constant, what are the units for the constant? We're going to find out. And then we have frequency, which is our hertz. Hertz. Okay. Remember that hertz is equal to 1 over second. Okay, so it's the number of times a cycle happens in a how much time it takes for one cycle to happen. Excuse me. So we have our centimeters, which is equal to the mysterious unit over hertz. What I'm going to do is just replace hertz with 1 over second. Okay, so we have our wavelength is equal to our mysterious unit over 1 over s. And remember, okay, so this is a reminder. When dividing by a fraction, just multiply by the reciprocal. Just multiply by the reciprocal. Okay, and so we'll have centimeters. Whoops, let me continue to use the same colors. So centimeters is equal to our mysterious unit that we don't know, but instead of divide, we're going to multiply by the reciprocal, so it'd be s over 1. Or we could just say, since it's s over 1, it would just be s. Now we want to get the mysterious unit by itself, so we're going to try and get rid of the s by dividing it on both sides. Okay? And so what we end up happening, or what we end up getting, is our wavelength unit over part of our frequency unit is equal to our mysterious unit, which is, so centimeters per second. So we have a distance or length measurement over time. And from first semester, yes, you have to remember things from first semester. We remember that this is velocity. So our k, which is a constant, represents our medium's wave speed, or I will allow you to call it velocity, so that it's much shorter to write. All right. And so some of you ended up with a velocity that was about 2,000 centimeters per second. So that means that for every one time that your string went back and forth, it happened at a time of 2,000 centimeters per second. I think, hold on a second. Yes, I believe that is true. If I'm wrong, please make sure someone corrects me. I do not want you to be learning the wrong things, and I will remake this video. And so now going back to our mathematical equation, so we're going to look at our prediction. Okay, so our prediction. So our equation was, let's see where our equation was. This was our equation. So we have wavelength is equal to our constant over frequency. And so since this was a number that you got, you're going to replace that. This was your x. This is x. So this is the one where you give it a value. Give a value and then solve using algebra. So we have our wavelength. We predict our wavelength to be at so if our velocity was 2,000 centimeters per second, and we wanted a frequency of 4 hertz, okay, then what would happen is we would expect our wavelength to be at a number that is 2,000 divided by 4, which is 500 centimeters. And then that would be your prediction section. If you have any questions, please always make sure to ask and let me know.